Chapter 19 is on the specifics for tests that we need. We are going to talk in depth about the testing method and what exactly we are doing in statistics when we are running a test. So the first thing we're doing is choosing a hypothesis. Now, when we choose a hypothesis, we choose a null to start. Now, the null is a statement about a population parameter. Population parameters are things like mu, sigma, p. These are all population parameters. A population parameter is a truth that exists. The true proportion of students that want a new restaurant on the strip. The true proportion of students that will stay after their freshman year at UT. This is a truth that exists. What we will do is look at the probability of our sample results or results more extreme than our sample results given that the null is true. So let's say UT wants to see if opening a new restaurant on campus is something the students would want. They might assume at the moment that, students are kind of half and half about it, 50-50. Do they have evidence that more than 50% of the students want a new restaurant to open on campus? With that in mind, if they start assuming that 50% of the students want it, can they find evidence that more than 50% of the students want it? We will choose our alternative, but we will do this before the test is run. In some instances, it wouldn't even make sense to choose an alternative that we could have evidence for. What if we are a researcher and we're trying to get more money for rabies research? If we want to show that rabies is increasing in America, that would probably garner us more money. Maybe the data leads us to believe that rabies is actually decreasing in America. Not that we don't want to prove this, but it's not going to help us out. It's not going to lead to more research money for us, and we definitely couldn't publish it. And it's not deceptive, but before doing any research, we said, let's investigate rabies, and maybe we are actually doing it in such a good way that we're saying, is there a reason to research it more? Because that's probably, we should do it in a moral way, such as, is there a reason to go about garnering more money for rabies research? Do we have evidence that rabies is increasing in America? Probably needing more money. So our alternative was chosen beforehand. Do we have evidence? And every time we say evidence, we're talking about an alternative. Do we have evidence to believe that rabies is increasing in America? And if you take a moment and think about the null, this null makes a lot of sense right here. The null for rabies, or the null associated with rabies increasing in America, would be that rabies is not increasing. That if it was at an incidence of 1 in 1,000 in America last year, which is probably way overestimating it, if it was at an incidence of 1 in 1,000 last year, it'd be at an incidence of 1 in 1,000 this year. And the alternative would be that the incidence of rabies is greater than 1 in 1,000. So the null is pretty much what we would believe without any evidence. If someone said, how do you think the rabies numbers are this year compared to last year? You'd say, the same. I don't know. I don't know anything about rabies. So until I am given evidence that it's increasing or decreasing, I would believe that it's staying the same. So staying the same is a lot of times the best null. Let's think about p-values, because p-values are everywhere. They're in research. They are extremely important to our cause in statistics. So the p-value is a conditional probability. When we look at it, it's very important that we realize that the p-value is always based on our null being true. To be specific, the p-value is, and this is a good thing to write down, the probability of our results or results more extreme happening due to random chance variation, given that the null is true. So we're saying our sample results could happen this percentage of the time due to random chance, given that the null is true. The null is always going to be at the center of your distribution. Because think about this. The center of your distribution is the most likely thing to occur. And if the null is true, wouldn't it be the most likely thing to occur? It's saying, if you assume the null is true, what should you see? Well, you would expect to see the null or something near the null. But now think about this. If our sample results are far away from the null, like they land nowhere near the middle of that normal looking curve, they don't land near that center hump, they land way over to the right, what would you think then? You would think that maybe the null is wrong, because we shouldn't land so far to the right. Now with these small p-values, they could have just happened by chance, given that the null is true. And we could continue to believe the null. But what if I told you there's only, the probability of our results or results more extreme happening due to random chance variation, given that the null is true, is 1 in 10,000? You might say to me, well, given that null is true, I don't think we would observe our results. And yeah, I don't think so either. So what would I do with that null? I would reject it. And to reject the null is pretty much to say, I do not believe the null. I am much more likely to believe some alternative. So we often say, I reject the null and I show evidence for the alternative. We will do that when our p-value is less than the value of alpha, which in most cases is 0.05. So with this in mind right here, when we have a big p-value, that means that our results could have happened given the null. I mean, it's like, well, the probability of our results or results more extreme happening due to random chance variation, given that the null is true, is, 50%. Yeah, that's probable. That could have happened given the null is true. So, yeah, I will continue to believe the null until given evidence otherwise. Now, choosing your alpha level is very specific. This is an important part of your test that must be done beforehand. Usually, we have an alpha level of 0.05. So this is chosen before the test even starts. And this alpha level is going to be the area shaded under the curve for which you will reject. We can choose something smaller, we can choose something bigger. We are going to call this the significance level. And when something falls below the alpha level, we will call it statistically significant. So once again, in most instances, your alpha level is 0.05. So you can call that a 0.05 level of significance. And anything that falls below 0.05, generally, we would say if it's at 0.049999 repeating, it is statistically significant with an alpha of 0.05. So once again, if something is at 0.03, that is statistically significant with an alpha level of 0.05. Now, we have other common levels of alpha. The 0.10 is not as common as 0.05 or 0.01, but it still is used. This is, as I said before, your significance level, and it's still just your alpha level. And as we see at the bottom, we reject the null. We say that the test is at a certain significance level. It's important for people to know this because you might just say at times, I reject the null with a significance level of 0.40. Now that would be a very bad thing to say because that means the probability of our results or results more extreme happening due to random chance variation, given that the null is true, well, at least for us, was less than 40%. And if I tell you there's a 40% chance it'll rain today, that doesn't sound unlikely. These results right here, these levels of alpha, would indicate results that are unlikely to happen due to random chance variation given the null is true. Our results must have been far away on that curve from the center. So we would reject the null because it's far away. We choose small alphas. Now, choosing your alpha would be dependent on what you're doing. If you're working for Nike and you want to show that Nike shoes are better than Reebok, I'm not saying they are, I'm just trying to remember which way to our context. Yes, we're on Nike now, I think. So let's say you want to show your Nike shoes are better than Reebok shoes. Well, do we have evidence? Wait, I just said evidence. So the null would be that Nike and Reebok are the same. The alternative would be that Nike shoes are better than Reebok, because I need evidence for that. I would assume things are the same until given evidence otherwise. With this in mind, I could probably use the alpha level of 0.10. Does it really matter if I don't have strong enough results? I'm not changing the world here. I mean, it's not the end of the world if I say something that's not true here. More on that later. But what if I'm doing medical research and we have a new technique and we want to show that the new technique is better than the old technique. So we want to have evidence that our new technique is better. With this in mind right here, what if we make a mistake? What if we don't have enough evidence? Well, we should probably require stronger evidence. Lower alpha levels require smaller p-values. Smaller p-values mean stronger, more significant evidence. The lower your p-value, the more significant it is. And these alpha levels require you to have a lower p-value to reject the null. So with this in mind, the p-value gives your reader far more information, and I always state my p-value because even if you set your alpha to 0.05, you can reject with a p-value of 0.04 or a p-value of 0.000001. So you always provide your p-value. Frankly, and I'll just say this, all I need is your p-value. And like as a reader, if I just see someone's p-value for a test, I can make my own decision about what's significant enough and if they should have evidence or not. Now, when you're writing your report for a journal or something, you probably need to say if you thought you had evidence. That's very important to your decisions. But as a reader, I might say, oh, they only used an alpha of 0.10. Well, I don't like that. That's not strong enough evidence. And look, they had a p-value of 0.08. Oh, that's not really strong evidence. I one time saw in a book where it had weak evidence, 0.10, statistically significant evidence, 0.05, strong evidence, 0.01, empirical evidence, 0.001. And these aren't, and this is just my memory of it, but these aren't strong, hard and fast words that we would use for those things. It's just someone trying to give an understanding of as the p-value gets smaller, you have more evidence. We still use reject the null and fail to reject the null because it aids in us doing write-ups and making decisions about if we have enough evidence, which is very important because that'll lead us to do more research, make decisions about the way science is going, nursing, medicine, marketing. All these things are based on making a decision on your null and when to reject if you think you have strong enough evidence. So once again, you will pick your alpha level before running a test. What is strong enough evidence for me? And if you believe you have strong enough evidence afterwards by looking at the p-value, then you would make a decision based on that. Now, we have something here. We've been talking about statistically significant this whole time. Statistically significant just means that our p-value is lower than alpha. Now, we have instances where something can be statistically significant but not practically significant. If I research 100,000 students from all around the United States, and I find out that there is a statistically significant difference between the grades of right-handed students and the grades of left-handed students, that means that what I am observing did not happen by random chance variation, given that the null is true. And the null for this would be that the grades of right-handed and left-handed students is the same. Let's say I want to find evidence that left-handed people have higher grades. Sorry, right-handed people. I'm in your group, but sorry, we're going against you guys these days. So with this in mind, let's say the GPA difference is 0.001, 1/1000th of a point. Now with large amounts of data, we can often find something that is statistically significant, but not practically significant. Because think about this, if someone told you, left-handed students make better grades, it's been statistically proven. Now, statistically proven is probably a bad thing to say. It's been shown to be statistically significant. Because we don't really prove anything in statistics, we just show evidence or more evidence. And with that in mind, would you want your child to be left or right-handed? If they say there's statistical evidence to show that people who are left-handed make higher grades, you say probably, well, if they're left, that'd be great if they're left-handed. And there's probably a lot of other things you have to deal with if you're left-handed that might counterbalance that. But on grades, at least, it might be helpful. But here's the thing. The difference we observe is 0.001, 1/1000th of a point. Does that really sound that practically significant? That the GPA is going to increase by 1,000th of a point? Small numbers can be statistically significant. All it means is that the p-value for the results is less than 0.05. That's all statistically significant means. It doesn't carry any weight on what the number is. It could be that the difference was 0.5 and the half, is that practically significant to you? Half a GPA point from 3 to 3.5? That sounds big to me. What about 2? From all the way from a 1.5 to a 3.5. Now that's really big. But what if our sample size was really small now? We only took 2 students in our sample. Now a difference of 2, although practically significant, is not probably statistically significant. Because if you take 2 people, and this is where it all ties together, I think, if you take 2 people, couldn't it just have happened by chance that the one had higher grades than the other? That's what we're saying here is, that's not statistically significant to take 2 people and observe a big difference. Probably taking 100 people and observing a big difference would be statistically significant, because that wouldn't happen by chance. We are very exact in our words here, because when we talk about statistically significant, we are saying the results we see did not happen by chance, given the null is true. And if you take 2 people, you can sometimes see a big difference, but that probably just happened by chance. Let's go collect more data and see if it didn't happen by chance. So, confidence intervals and hypothesis tests. They are linked in every way you can imagine. As we've seen, confidence intervals and hypothesis tests are built from the same calculations. They have the same assumptions and conditions, and you can actually approximate a hypothesis test by using just a confidence interval. All you're going to need to do is just look to see whether the null value is inside that confidence interval. The confidence interval is specifically going to correspond to a test done with an alpha level of 100 minus the confidence level. What this means is you will have a 2-tailed hypothesis test with an alpha level of 0.05 if you make a confidence interval that is 95%. Plug in 95% right here, and you get 100 minus 95, and you'll get 5 for your alpha level, which is 0.05, 5%. This is a 2-tailed, or 2-sided as we say sometimes, test. This is the does not equals test. A does not equals test corresponds to a confidence interval with 1 minus the confidence level. So once again, if we make a 90% confidence interval, we could use a 2-tailed test to reject at the 0.10 level of alpha if the value we're interested in is not in the confidence interval. A lot of times this value is 0, and this is usually for a 2-sample test. When testing 2-sample means, we are often concerned if the value between the difference of the means is 0. If 0 is not in our confidence interval, we could reject the null at an associated level of alpha for a 2-tailed test. That associated level of alpha would depend on how big our confidence interval is. If it's a 98% confidence interval, we could reject at an alpha of 0.02. If it is a 99% confidence interval, we could reject at an alpha level of 0.01 on a 2-tailed test. Now, oftentimes in statistics, we make mistakes. And the mistake we make is when we choose to reject the null or we fail to reject the null. A type 1 error is when the null hypothesis is true, but we reject it. In our Nike and Reebok example, this means the null was there is no difference between Nike and Reebok shoes. But we mistakenly reject it. Aha, our Nike shoes are better. In a type 2 error, the null is false. Now think about this. The null was Nike and Reebok shoes are the same. But we are going to fail to reject it. By failing to reject it, we're staying with it. To fail to reject the null basically means to stay with the null. I'm going to continue to believe the null. I'm not going to have evidence against it. So what was the truth? Right here in this graph, you can see the truth in a type 1 error, we have that the null is true. But what did we do to the null? We rejected it. This is a type 1 error right here. The null was true, which means Nike and Reebok shoes were the same, but we said, aha, we have evidence against it. Over here, we make the right decision, and so do we here. because the truth is that the null is true, and we kept it. We stayed with it. We retained it. But what about if we stay with the null, retain the null, and it was false? That is a type 2 error. In a type 2 error, we would say that we fail to reject the null, but meanwhile, the null was false. A type 1 error has a specific level of occurrence. A type 1 error is going to be associated with our alpha level. The alpha level is when we choose to reject the null. So remember, this is the degree of evidence we need to reject the null, which means we have complete control over it. We can pick our alpha level, so we can pick how often we expect to see a type 1 error. In a type 1 error, we reject the null, but the null was actually true, and we should not have rejected it. Now, a type 2 error is a little bit different. In a type 2 error, we can't pick how often it occurs. A type 2 error is based on beta. Beta is not 1 minus alpha. Beta will be based on 3 things and will be associated with the power of a test. And we'll see more on that in a moment. But first, let's review type 1 and type 2 error with a few more examples.
Sometimes our choices have consequences. Think about it for a moment. What if you're a pirate and you're about to go out on your pirate adventures? Well, you might go see a doctor first. The doctor is going to assume that you are healthy. This is very important because the null hypothesis here is you are healthy. Let's repeat. The null hypothesis for the doctor is you are healthy. Now, when you go in, you ask for a test for scurvy, common pirate disorder, disease, whatever it is. With this, they're going to see if they have evidence that you have scurvy or there's no evidence you have scurvy. The test will either come back positive or negative. If the test comes back positive, there's evidence you have scurvy, and you're not going to go out on your great adventures. If the test comes back negative, then there's no evidence you have scurvy. You'll go out on your great adventures. But think about this for a moment. Do tests always get it right? What if the test comes back negative? You go out on your adventure, but it turns out you do have scurvy. What if the test comes back positive and you don't go on your adventure and you miss out on all the fun and you don't have scurvy? What we're talking about here is a type 1 and type 2 error. In the type 1 error, we reject the null because we believe we have evidence. It's a false positive. Just like on that test, we got a false positive saying you have scurvy. You would not go out on your adventure and there would be consequences. In the type 2, the test comes back negative, a false negative. We do not have evidence that you have scurvy. And you go out and your pirate adventures end a little quicker than they should have. Now, a type 1 and type 2 error, it's not always that one is worse. It depends on the situation. If you think about a teacher and a student, the teacher might assume that all of their students are good students until they have evidence that a student is cheating. In this instance, the null is the student is a good student. What if we reject that null by mistake? We're going to say the student is cheating when they're actually a good student. What if we fail to reject that null? A type 2 error. We're going to say that the student is a good student because we don't have evidence otherwise, when they're actually a bad student. The type 2 error, where we say that the student is a good student, would actually be better for the student. And they'd be a dishonest student, but they wouldn't get caught, so they'd probably like that. We as the instructors would not like that because a student's getting away with cheating. Where in a type 1 error is really bad for the student. Think about this. Your instructor comes to you and says, I have evidence you're cheating. They are rejecting the null, saying they have evidence that you're cheating. Right here, that's not a good situation to be in because in a type 1 error, the evidence they have is not the truth. It's a false positive, and you weren't actually cheating.
Okay, so what are the 3 things that affect the size of beta? Well, the effect size is one of them. The effect size is the actual difference between the null and the truth. Now think about this. In a type 2 error, we fail to reject the null. With this in mind, we should have rejected it. The effect size is the actual difference between the null and the truth. So in an example right here, what if you have two basketball players? It's going to be you versus your friend, and you're both about at the same skill level. If you were to shoot free throws, well, could you figure out who is better if you are both about the same? It might be pretty hard. You might kind of figure it out after a while. But what if you went against Michael Jordan? Would you be able to see who's better between you versus Michael Jordan? I think it'd be pretty easy. Michael Jordan's probably still pretty good at basketball and could, I assume, win against most of us, or probably all of us, I would think. What if it was you versus a kindergartner? In the second examples right here, the effect size is big. Michael Jordan is way better than us. A kindergartner is, I would assume, way worse than us. Maybe not me, but probably way worse than you. What if we put Michael Jordan against a kindergartner? Would it be easy to see who's better? It would. We start out assuming they're the same because if someone said, Brian Stevens versus Michael Jordan, and we asked someone who didn't know either of those people, which would be hard to find, they'd say, I don't know who's better. They're probably both the same. You want me to place a bet? Brian Stevens, his name sounds nice. But in truth, we all know Michael Jordan is better, and it'd be easy to find evidence for that. So with this in mind, the effect size is the difference between me and Michael Jordan. The null assumed that there was no difference between us. And that's the null. There's no difference. The truth is there's a huge difference. What if we put me against one of my friends? The null is that there's no difference. The truth is that there's a small difference. So the effect size, the difference between the null and the truth, is really small between my friends and I, but between me and Michael Jordan, it is much larger. So the larger the effect size, the smaller beta will be. And remember, beta is when we fail to reject the null. So if we have a large effect size, it's really easy to reject the null. It's really easy to reject the null and say, no. Michael Jordan is way better than Brian Stevens. Now, I know earlier I said that you can't calculate beta from alpha. And that's true. You can't calculate beta from alpha with just alpha. But alpha does influence beta. And what happens here is this. Alpha is the degree of evidence you require. Alpha is going to be, I have this much evidence, that's good enough for me. So what if we just said, let's set alpha equal to 100% or 1? That means we can reject the null at all times. Now that would be a horrible mistake. But think about a type 2 error. In a type 2 error, we fail to reject the null. So to have a type 2 error, you have to fail to reject the null. That is a requirement. A type 2 error, you fail to reject the null when you should have. If we set alpha to 100%, we can just reject the null at all times. We'll never fail to reject the null. So you'll never mistakenly say that there are not results when there are. This would be a very bad idea, and you'd make a ton of type 1 errors. As we say right here, the more you are willing to accept a type 1 error, which is rejecting the null when you should not, the less likely you are to make a type 2 error. Because in type 1 error, you're rejecting the null. So if you reject the null, let's say all the time, well, then you can't make a type 2 error where you fail to reject the null. For our basketball examples right here, imagine we're trying to say who's better at basketball. And we put me against Michael Jordan again. And after one round of play, just like one free throw each, we say, Michael Jordan's better. Well, in that instance, we didn't even make a type 1 error. Well, it would seem to me we did not. But we rejected the null. But what if we put me against my friend and I shoot one shot and we say, we have evidence your friend is better. Because I, of course, missed my shot. We have evidence that your friend is better than you. In this instance, we had a very low threshold of what better was. We were willing to accept very little evidence to say someone was better. The null was that we're both the same. The alternative was that one of us is better. And we said we had evidence almost immediately. Now, we could have made a mistake right here. We could have made a type 1 error. But we did not make a type 2 error. The type 2 error would be to say that we're both the same when we're really not. Now, we're not even talking about what the truth is here. It could be the truth that one of us is better. But we can't make a type 2 error when we reject the null. So Alpha is when we reject the null. If we increase when we reject the null, thereby rejecting the null more often, we can't make a type 2 error. It makes beta smaller when we make alpha larger. Finally, sample size. And this one we've been talking about since the beginning, when we talked about going out and talking to UC students and talking to more and more. When we talked about left versus right-handers and we said, well, you could talk to 2 or you could talk to 100. Your results are stronger with more samples. So with this in mind right here, if we were to take 2 free throws each, would we really understand who is better? If we were to take 100 free throws each, would we understand who is better? And by 100, we probably would know who is better if my friend took 100 and I took 100. This is actually going to decrease our chance of making any sort of mistake. It's going to decrease our chance of making, more specifically, a type 2 error. In this instance, if we say we're both the same after all these results, after 1,000 free throws, would you think that would be believable if my friend and I make basically the same amount after we look at 1,000 free throws? Tiring day. But what if we say after 1,000 free throws that we have evidence that one of us is better? I would say, well, that sounds like you did enough to show who's better. Now think back. What if the difference is that my friend is 1% better at free throws than I am? When it comes down to playing basketball, would that really matter if he's a 51% free throw shooter and I'm a 50% free throw shooter? I don't think so. That's a very small difference, and my friends might say, well, okay, it's statistically significant he's better than you, but maybe we like these aspects about Brian, like he's really strong on rebounds, and they might say, well, that's not as practically significant as we'd want it to be, going back to the idea of practical significance. This is just about statistical significance here. And when we increase the amount we sample, we are less likely to make a type 2 error. Now, the effect size is something we cannot control. The effect size, as we said, is the true difference between the null and the truth. There are things we can control. We can control our alpha level, and we can control the sample size. What we're looking at with all 3 things is power. The power of a statistical test is the ability for it to correctly reject a false null. Remember here, the power of a statistical test is its ability to correctly reject a false null. So beta is the probability of a type 2 error. Beta is a type 2 error. In a type 2 error, we fail to reject the null when we should have. So 1 minus beta is power. Basically, the complement of making a type 2 error is the power of a test. Everything but making a type 2 error. Power is based on the 3 things we mentioned: sample size, effect size, and alpha level. As mentioned previously, when we calculate power, we imagine that the null hypothesis is false. We are basing the power of the test on how far away the truth lies from the null hypothesis. With this in mind, this is going to give us the effect size. The power directly depends on the effect size. So we can calculate the power of a test. We have to assume an effect size. We will choose an alpha level before running our test. We will have a sample size from how much we went out and collected. And then we would have to pick an effect size and say, what is the power of our test with this given effect size? It doesn't mean that the effect size is true. It's just what we are assuming to run a test. We, in most cases, will never know the true effect size. So let's look at an illustration of power right here and see how it increases and decreases with given levels of alpha. This curve right here seems a little bit complicated, but realize over here on the left, we are looking at power. And let's review for a second that over here, we have a 0.05 level of alpha and a 0.10 level of alpha. The top curve is going to be a higher alpha level. This one right here, this blue one, is an alpha level of 0.10. And remember we said, when you increase alpha, you increase the power of a test. This is because you decrease beta. When beta is smaller, you'd be subtracting a smaller number right here and power would be bigger. Just put beta at 0.01, that makes this 99. Put beta at 0.20, this makes this 80. So when beta is smaller, you increase the power of a test. And when you increase alpha, you decrease beta. They have an inverse relationship to each other. What this is showing you right here is possible values of the truth, the true proportion. So as we go further away from our null right here, which is what we believed, the power of the test is going to increase. This is our ability to correctly reject the false null. And think about this. There is a difference right here. There is a difference even at here, but we can't detect this difference. Power is basically the ability to detect a difference because we can reject the null and say there is a difference. When we have this, we could also make the test more powerful and make these curves sharper if we were to increase sample size. This graph right here assumes a constant sample size throughout. If we were to increase sample size, these curves would get closer to the center. They would swoop in a little bit because we would be more powerful at all associated levels of P. So let's think about power here for a second. So we have a very large shipment of rivets that are arriving to work where a bridge needs to be built. We take a random sample. So if the percent of rivets in this shipment that are defective is 1% or greater, we're probably going to have an unsafe bridge. So we need evidence to show that these rivets are defective and we probably need to send them all back. We can't just, you don't get a shipment of rivets in and say, these are all bad. You don't even look at them. You don't even look at them. You say, these are all bad rivets. Let's send them back. You'd say, we need evidence that the rivets are bad before we're going to send them back. So our null would be that the rivets are good. That we could say, well, let's assume 1% are defective and then try to show evidence that greater than 1% are defective. And technically, if you're concerned about 1%, you could set it to 0.99999% are defective. But 1% is, we'll just go with that and see if there's any sort of evidence. We can look at the p-value, and if it's exactly at 0.05, still with the bridge, I wouldn't build it. I'd say, no, I'm a little hesitant still. And this is a bridge we're building. We'll talk more about that in a second. So the null is going to be that 1% are defective, and then the alternative would be, do we have evidence that more than 1% of the rivets are defective? In context here, a type 1 error is when we reject the null. So what does this mean? This means we reject the null. The null was that 1% are defective. If we reject that, we show evidence that more than 1% are defective. But a type 1 error means we made a mistake here. It turns out that we didn't have evidence that more than 1% are defective. We were wrong to believe that. So we send the shipment back. It takes a few days, and it's annoying. But we were wrong, and they say, no, these are good rivets. We tested them through our machines again. What about type 2 error? In a type 2 error, we fail to reject the null, and we say that they're good rivets when we should have rejected the null. The null was actually false. We build the bridge. Bridge falls apart. That's horrible. We would not want that to happen. So type 2 error right here has big problems. And remember, it's not that a type 2 is always worse. It's contextual. The power of the test is the ability to find out that we should send the rivets back. When we have a powerful test right here, we can detect bad rivets. And if we're really concerned about it, we should probably sample a lot of the rivets. We should put a lot of them through our stress test. We should also be very careful in what is enough evidence. We could set our alpha level to 0.20. And you might say, whoa, don't do research at the 0.20 level. But we're building a bridge here. If we have any sort of evidence that the bridge is going to fall apart from these rivets, we might want to say, let's send the rivets back. Because the consequences of a type 2 error is going to be devastating, literally. Type 2 error, we fail to reject the null and we build the bridge with unsafe rivets. Where type 1 error is we're going to send the rivets back. So we do not want to make a type 2 error. So let's put all of our power into rejecting that null. Let's try as hard as we can to reject it. Any sort of, if you're worried a little bit, you reject the null. And that's what we mean by the power of the test right here. If I was traveling over that bridge, I'd be very, very concerned about a type 2 error. In a type 2 error, we fail to reject the null. The null was that the rivets are good. And both of these errors could be made smaller by just sampling more. Because when you sample more, you are going to impact the strength of your results. If we were to sample, we got a shipment of 100,000 rivets, we're going to have better results from sampling 10,000 than we would sampling 1,000. Always sample more unless we're going to break the 10% rule, which 10,000 would be right under 100,000. Even then, the 10% rule is just a guideline. If you were to sample 11,000, your numbers don't blow up in your face. It just works with the error in the math calculations. So with that in mind, more samples means stronger results. And you'll usually see that. And for a lot of instances, especially for rivets, I go back on the 10% rule now, because if this company is constructing rivets, then the population of rivets is pretty infinite because they can keep constructing rivets. So we're not actually going to oversample the population of rivets if there's probably a lot of rivets out there, and then we could even say that it's pretty much that infinite rivets could exist. So the numbers are going to be a lot stronger if we go out and sample 10, 20,000 of the rivets from the company. This is the end of the lecture. Good luck.